Or at least for you to know from our face.
You're excited, I can tell.
There we go.
Despite the 1,000-yard stare. All right, part 2 of Kubas. Here we go. The first part was so exciting we lost 2 of the audience. All right.
They have the research symbol about it.
Yeah. So I guess just to back up one more slide. So they're trying to, I guess, determine the coordination of hydrogen. We talked previously, hydrogen's kind of hard to find because it's tiny. It's going to be sitting next to a much larger metal, which is going to be able to obscure it based off our detection methods. So X-ray becomes problematic, and neutron is generally what's used as far as neutron scattering, which looks at the nucleus instead of looking at the electron cloud, which is what X-rays look at. So again, this is an example of the hydride compound that had been in the literature, and there had been debates between different research teams as far as what structure it had. And so the debate was whether it was this structure, which was similar to the iron pentacarbonyl, where the carbonyls are still in that same trigonal bipyramidal setup, and then the proton's kind of just stuck onto one of those faces, so it's embedded in the d orbitals is how they say it. Or whether it was actually a coordinating ligand insofar that it messed with the geometry. And so this was the other proposed one where it was more octahedral in nature, similar to the hexacarbonyl compound that manganese normally adopts. So based off of what they were able to find, it adopted the octahedral setup as opposed to the trigonal bipyramidal one based off of the structural analysis. So they did that one. This was the other one that was looked at the time as rhenium hydride, as a rhenide anion. And that's another case where there's a whole bunch of hydrogen coordination to the rhenium on the right-hand side. This is just that structure showing the potassium and layers of the cations and anions. So what we care about is this complex that Kubas initially synthesized. So they had made this compound previously, a year before. Has a very deep purple color to it. By simple application of hydrogen gas, and I believe that they state in the paper, generally they use 1 atmosphere or more as far as the pressure goes, but they can produce this manganese compound where the hydrogens come in and is now bonding in an 8-2 fashion. So no other ligands fall off. It ends up just being a rearrangement. So we can probably consider this guy being trigonal bipyramidal. Most likely those 2 phosphines and then one of the COs are in the equatorial. The other 2 smaller COs would be in the axial. So when this hydrogen comes in, it's going to force this guy to adopt what looks to be a little bit more octahedral in nature. So we got our metal in the middle, and then as far as coordinations, we have 1, 2, 3, 4, 5, and then we consider the hydrogen our 6, so now we have a kind of octahedral setup. For this compound, as far as just the name goes, so the trans is looking at the phosphines. So these phosphines are on opposite sides of the tungsten. That's where that portion of the name comes from. You guys remember MER, maybe from 311. MER means you're lying along the meridian. And so the CO, CO, and CO are all along an equatorial plane or along the meridian in this case. The other way that you can have it is where the 3 sit along the face, and so you'll see FAC instead of MER. But this would be the meridial setup. I believe Mallory was asking why they showed both lines in the X-ray crystal structure drawn from the hydrogen to the metal. Again, that's supposed to imply the 8-2 coordination. So normally in class when we've been drawing them, we've drawn the arrow from the middle of the bond down. So in this case, I'm just trying to mimic what the paper has, where we're just trying to show that both of these hydrogens would be coordinated symmetrically to the tungsten. So this is a very easy reaction to follow, mainly because of that color change. So it goes from deep purple to yellow. They were able to isolate crystals of this analog. So they had problems with getting the crystal structure for the cyclohexyl phosphine. They had a little bit better of a time using this isopropyl phosphine. So the only thing that's changed is the R groups coming off the phosphorus in this case. So it's going to be a little bit more sterically enhanced, I guess. I'm not sure why that would lead to better crystals, but there you go. As far as looking at the structure, the cis ligands, so again, this is going to be an octahedral setup, so every ligand should be approximately 90 degrees if we have an octahedron, and that's actually pretty good from what they saw between the donating atoms. That was got between 88 and 92, so it is really close to being octahedral. As far as the metal hydrogen distance, if they use X-ray data around 1.95, for most of these studies, we'd probably rather believe the neutron one. It's probably going to be a little bit closer to reality just because it's going to be a better detection method for hydrogen being so small. So around 1.75 angstroms for the metal hydrogen distance. Contrast that with the hydrides that we just talked about. The hydrides are generally going to have a closer contact with the metal. Normally, if you're a hydride, you're going to be below 1.7 angstroms. That's that 1.6 to 1.7 range that we have there. So this is a little longer than that, so it's a little bit outside of that normal hydride range, which means that it's probably a little bit slightly different coordinating mode. The other thing that lends credence to the fact that it's H2 coordinating and not two dihydrides is the HH distance. So free H2 has 0.74 angstroms. If we compare that to X-ray, slightly longer, again, neutrons probably a little bit more believable. But the idea is that when it coordinates, remember it donates those two bonds, and it's also going to have electron density from the metal going back into the anti-bonding sigma star because that'll line up with the symmetry for the d orbitals. And so that's going to effectively reduce the bond order and elongate it. So that's why we see an increase from 0.74 by about 0.1 angstroms up to 0.84. It is symmetrically bound, so one hydrogen is not closer to the tungsten than the other one is. They're both approximately the same distance away. And the H2 is parallel to the phosphorus-tungsten-phosphorus bond. So this guy would be flat, let's say. That means that the hydrogen sits flat on top of it. So they're parallel to each other. So this was the crystal structure data. They did both X-ray and neutron. The X-ray, like we said before, to even get decent data for X-ray, you have to go to super low temperature. So for this case, they went to -100. But you can imagine the setup for doing these types of experiments is relatively difficult if you have to go to both low temperature and as well as keeping generally some kind of hydrogen pressure above the compounds so that it doesn't decompose. And growing the crystals, I'm sure, was fun as well. As far as other data, if they looked at the IR information, so as far as the different things they can look at just the hydrogen-hydrogen vibration, so as it just sits there as a spring going back and forth. They can look at the asymmetric and antisymmetric and symmetric vibrations of the hydrogen actually being bound to the tungsten. So the symmetric, you guys remember H2O, symmetric versus antisymmetric. So symmetric is they both go out at the same time, antisymmetric is one comes in. So the idea is that the symmetric H2, whatever ligands on the opposite side, which is going to be the CO, they would be going out at the same time and coming back in. And then the asymmetric, they'd both be going up and they'd both be going down. For the delta at the bottom, that's going to be torsional, so that's generally going to be it tilting off of its axis a little bit. So as far as looking at the data, they looked at 3 different analogs. So they used H2, then they deuterated one of the hydrogens, and then they deuterated the second hydrogen. As far as these guys go, most of this is infrared. Some of these where the R is noted, that stands for Raman. But in general, your frequencies end up being approximately the same. Some vibrations are IR active, some are only Raman active, some are active in both. But to look at the data, free H2, I don't think I have it on here. Doesn't look like it. But generally, free H2 is going to have a frequency that's easily above 3,500 as far as the wave number goes. So the fact that it decreases a whole bunch again, kind of tells us that that bond order has gone down a little bit, just like when we talked about with CO, how CO will go from 2143 as far as free CO has a triple bond. As soon as it coordinates, generally the frequency drops because it's going to more double bond character. So same thing with the hydrogen. It bonds, we don't break any of the bonds, but we certainly do make that bond a little bit weaker based off of IR. As far as comparing these analogs, when we go from hydrogen to deuterium, what's really happening? What are we changing? Mass. So we're making this thing heavier. You guys know that lighter things are going to be able to vibrate faster. As we add something heavier, we're going to make that vibration decrease in intensity. And so that's why we see these values go down a little bit for replacing one, make it even heavier, makes it go a little bit slower, so it goes down even further. So this isn't surprising. This is what we expect as far as the step down goes. Looking at these other ones, for the symmetric and the asymmetric ones, similar as far as decreasing in intensity, so that's not really telling us much. The thing that they really got out of the IR data was that when you look at hydrides, the hydrides are generally going to have low frequency delta or deformation in the 700 to 900 region. There's nothing ever below that for normal hydrides. So when they saw that they were getting these kind of strange, really low intensity bands, they couldn't specify one for HD. They stated that it was obscured, so they couldn't put a value on it. The fact that they're seeing these indicates that there's a different coordination mode occurring here. So it's not a hydride, it must be this more A-to-2 coordination because these don't appear in a pure hydride spectrum like they had seen. So again, IR is not really great. It's good about kind of fleshing out groups here and there. It's really good though when you have signals that are present that aren't present in another spectra. So that's really what they were able to get out of this. What really lent credence, other than the X-ray neutron data, the IR was somewhat helpful, but not really, was the NMR data. So spectrum for the NMR was taken in D9 toluene, so this is where we replaced all of the hydrogens on the ring, as well as the 3 methyl protons, replaced all those with deuterium, so we got 9 of them on there. I've never actually seen D9 toluene ever, so I thought it was a strange solvent, which is just why I have it up there. You don't normally see this used. You guys ever seen tau? You guys have discussed NMR in any prior class? Okay.
It's chemical shifts?
Yeah, so you guys see this thing. So the two scales that NMR employed in the early days were tau and then delta. And pretty much everyone at this point has gone to the delta scale as far as the traditional parts per million shift that you see on the bottom. So the tau shifts here, 7.88, 8.86, and then 14.21. Now, if this is proton NMR, what are we looking at as far as this compound goes?
So you got the hydrogens off of the methyl
Okay, so
up on the phosphate.
methyl H's. What else we got?
You got your H2.
You got carbon misery.
We got H2. And then we have the hydrogens that aren't shown, right? We have all these methyls, but then we have a single hydrogen that's coming off of that carbon that's not shown. So we also have, what do we want to call those? I'm just going to call them isopropyl H's. Okay, so we have 3 different things. We have 3 different signals. That works. Now, as far as the NMR that you guys are used to working with when you guys look at deltas, if you saw something up around 7 or 8, what does that normally make you think as far as what's there? Yeah, normally makes you think aromatic. Obviously, we don't have any aromatic protons. And if you see something that was at 14.2 on a delta scale, what would that make you think? Other than your spectra's probably wrong. Right? There's something wrong with that. So how you get these, how you get ppms or delta scales for tau, is you do 10 minus. And so if we do 10 minus 7.88, that'll give us 2.12 parts per million. 10 minus 8.86, that'll give us 1.14 parts per million. If we do 10 minus 14.21, well, that's a weird one. We get negative 4.21. Now, at least 2 out of 3 of those make sense with regard to what you guys are used to. So this 2.12, that's obviously going to be those isopropyl H's. Mainly because they're going to be sitting on a carbon that's close to this phosphorus. That phosphorus is going to suck a little bit of electron density away from it, and so it's going to de-shield it slightly. The 1.14, very traditional, as that's seeing where you get methyl protons. And then the strange ass negative 4.21 is going to be our H2 guy. So when we go to higher numbers in the delta, then generally we say that we're de-shielding, we're removing electron density away from around that proton. And so if we are closer to 0, or in this case below it, and negative, that means we are heavily shielded. And so this is the idea that these protons, or these 2 hydrogens rather, are sitting really, really close to this tungsten, which has a whole bunch of electrons sitting around it, which are going to effectively shield it. So that's why we see that really strange upfield shift at -4 for these guys. Now again, that's not really different from what you see for hydrides. Hydrides also generally end up being in the negative region. So what really clinches it, at least as far as the NMR data goes, is looking at the coupling. So when you guys see J values in any of the literature, that means it's talking about coupling between 2 nuclei. So JHH means that we're talking about coupling between 2 protons in space. So coupling for organic compounds, for just normal sp3, sp2 type bonding that you would get, is normally between 6 and 8 hertz. That's pretty standard, at least between 2 protons go. So these are fine. What we really want to look at is the HH coupling for the H2 guy. So free HD, that analog that they made, has a signal of 43.2 as far as the coupling between the hydrogen nucleus and the deuterium nucleus. When they use HD and make that analog and have it suck onto the tungsten, this value goes down to around 33. Do I have that value on here? To 33.5. Now that's expected because again it's now bound to the tungsten. That changes its coupling a little bit, but it makes it go down by around 10 hertz. This is massively different than what you would get if this were a hydride system. So if this were a hydride, what you would see is that this guy would go down by around a factor of 10 is what they state in the paper. So that should be down closer in this range, most likely somewhere between 4 and 8 hertz or so. So the fact that they didn't get that low, again, is implying that those 2 hydrogens, or in this case the hydrogen and the deuterium, are still relatively close together, that there's still a bond between them. We haven't broken it and made it the 2 dihydride species. That makes sense? Ish. The other thing that you see is typical as far as splitting the 1 to 1 to 1. How familiar are you guys with Pascal's triangle?
Nope.
Nope. Okay. So just to explain that guy. So when we talk about NMR, the most common nuclei that we use with NMR generally have a spin of 1/2. And that generally comes from the fact that they have an odd number of nuclei. So for hydrogen, it's really easy. They have one proton, it has that spin of 1/2, i.e. they have a 1/2 spin. For deuterium, since we have that extra neutron in there, we end up having a spin of 1. So as far as the splitting that we get in the NMR signal, again, the idea is that these guys are little magnets, and little magnets, if they're relatively close in space, can talk to one another. And so if you can talk to one another, you can end up splitting your signal, or your signal can be split by your neighbors that are close to you. They'll affect your magnetic signal. So if we start off in each case with just a single line, Pascal's triangle, at least for NMR purposes, the math is 2Ni plus 1, and that's going to tell you how many lines you should get for a given nucleus. So you always start off with a single line. So if we have, I can't even spell neighbor correctly. If we have one neighbor, so n equals 1, we would have 1 times 2 times 1/2, which would be 1 plus 1 would give us 2. And so our single line is split into 2 lines. If we have deuterium and we have one neighbor, we would do 1 times 2 plus 1 would give us 3. Fine. And just to kind of keep going with this.
Oh yeah, I think I have seen this. This was like organic 1.
Neutral nano as well.
Yeah, I'm sure you guys have seen it. Should have seen it at least in both classes, I would hope. So if you go to 2, we'd go 4 times 1/2 gives us 2 plus 1, that gives us 3. And so what you end up having is that these guys would split, and you end up with boom, boom, and boom. Now, since these guys is split, technically there's a line from this dude and then a line from this dude. So I'm going to put a second line here in the middle. And this tells you the intensity pattern. So if you didn't have any neighbors, that's what is the NMR signal. This would be a doublet. And then since we have 2 in the middle, that's why the middle ends up being twice as big, and that's kind of your normal looking triplet if you're a CH2 group. And then if we go to n equals 3, we split again. And so we do 1, 1, these 2, 2, 2, these 2, 2, 2, this 1, 1, this 1. And so now we have 1, 3, 3, 1. And that's similar to what you get for if you have 3 neighbors around you. You get a little quadruplet. So that's traditional. That's what you get for if you have normal protons interacting with one another. So in the case for deuterium, it's a little bit different since it has that higher spin. So I just wanted to briefly give that just to tell you that that's why they get this HD analog and giving a 1-to-1-to-1 split here. So that's specifically that hydrogen is getting split by that nearest deuterium. There's one deuterium, it has a spin of 1, and so that's why you get those 3 lines, 1, 1, 1. But the NMR data was really important as far as showing that coupling, which if it hadn't been a hydride complex, it would have decreased massively from, again, this free value of 43, it would have gone down to somewhere around 4, 5, or 6. It doesn't, it only goes down by 10, so they're stating that that hydrogen-hydrogen bond is still relatively intact. Holla! Conclusions. Well, it's always nice to be first at something. My claim to fame is less important. I got to report on the first X-ray structure for a fatty acid methyl ester being bound to a metal. Woo! Nobody cared. But in this case, people did care about the hydrogen coordination because what it represents isn't really anything special other than it gives a little bit of insight into the mechanistic ability of metals being able to oxidatively add. So this A-to-2 coordination, we know that the hydrogen lengthens a little bit. And so it's more like we kind of arrest the development of that hydride, that cracking of that hydrogen-hydrogen bond, and so we stop it before it actually gets to that point. So it elongates it a little bit, but doesn't actually break it. And that's kind of the importance of these compounds. It's just showing that most likely for a lot of these oxidative addition reactions that we see in catalysts, that they're almost always going to go through some type of A-to-2 coordination first before actually cleaving the bond. The other thing that it really helped out with was basically being able to define structural parameters for these types of A-to-2 hydrogen complexes. And what they actually did, once this information kind of got out there, many compounds that had been reported prior to Kubas's were gone back and looked at again. And they were, they had been, let's say, called hydride species, but then it was later found out that they were actually A-to-2 H2s. And so there was a little bit of retrospective fixing of the literature as far as the structural parameters for some of these, based off of this paper and this work that was done. Questions, concerns? How awesome was that?
So why did they change the range in the NMR?
Why did they change the what?
The ppm.
So this is an older paper, so this is from early 80s, 84 I want to say. So at that point, we hadn't all coalesced around the delta system. And so this is just, you'll see it in older papers that they'll sometimes use the tau scale. But it's still the same experiment, it's still a standard normal NMR. It's just how the numbers are generated.
Why would they change it?
I'm sorry?
Why would they change it to the delta?
I'm changing it to the delta just because you guys are more
why
used
as
to
a general thing?
Yeah, why do we care to change it?
Oh, instead of using the tau? I think it's more one of those things where it's just, it seemed dumb to use two things to describe the same phenomena, so everybody just was like, all right, well, let's use one. I have no idea why delta ended up beating out tau, as far as why that scale ended up having predominance, but I'm sure that's the rationale for it. It's just like, well, it makes communication easier if we just settle on one thing.
I mean, we're still using like protons or what's flowing in the physics books, even on that kind of general idea.
Sure, fine.
We're still using like the old method for like which way current flows and like all the physics books and everything.
Yeah.
So, like,
What do you want to think of it as far as positrons or holes
now they
moving
decided
or
to change
whatever?
things.
But yeah, I can't give you any historical, I guess, information on that at all, though, as far as why we went with one versus the other. Anything else?
Yeah, when they do the crystal thing, when they crystallize it and they look at it, does it really look like the picture you have? Like, and you actually see the bones?
They don't imply, and I don't have the actual picture from the paper. So where they have like the lines connecting things, that's all, I guess, software editing after the fact. What they're getting from the crystal structure is just the distances between the atoms. And then based off of a library of prior structures, they're stating whether those bonds are going to be single bonds, double bonds, triple bonds, or if the distance is too great between them, whether they should be able to imply a bond at all. And so a lot of it's just comes from comparison to known compounds. But as far as those seeing the actual bonds, no, that can't come out from the X-ray. They just kind of get the general sense of where the atom is based off of its electron cloud, and then kind of go and retrofitting that manner as far as fitting the data. If you've ever seen raw X-ray data, it's basically unintelligible. It looks like nothing. It's kind of crazy how they can put together these very pretty pictures just based off of, all right, well, if we have if we have some amount of light impinging on this surface, and based off of where we think an atom is, it's going to redirect at some angle. So being able to fit all those reflections and spit out a structure, I still think is crazy. But yeah, they can't see the bonds. All they're doing is trying to fit it based off of what they know about the math and what they think the crystal structure is. So exactly, exactly. I don't even understand how some of it was done.
A lot of math.
Yeah, it's
painful.
This is why people devote their lives to their research.
Andrew's had us do like a bit of it.